All right, let's jump straight into it. If you're an AI engineer or a developer trying to get large language models to actually understand your company's proprietary data without completely hallucinating, you absolutely have to master Retrieval-Augmented Generation, or RAG. Today, we're going from zero to a fully functional RAG pipeline.
So we really need to address the elephant in the room first. Think about a cutting-edge LLM whose training data cut off in August. If you ask it about a massive company event that happened in September, it literally has no idea. But these models are hardwired to be helpful, right? So instead of just admitting it doesn't know, it hallucinates. It'll just invent a highly confident, completely fake answer. And in enterprise AI, that is a total showstopper. Here is our architectural blueprint for today. We're going to cover 1. Fixing LLM hallucinations. 2. The RAG solution. 3. The data ingestion pipeline. 4. Chunking and embeddings. 5. Vector databases. And finally, 6. The retrieval pipeline. Starting with Section 1, Fixing LLM hallucinations. Imagine you're building an internal HR bot for a startup. You've got all these private HR policies, leave policies, remote work eligibility, expense reimbursements. None of that is on the public web, meaning your LLM is completely blind to it. So how do I fix that? For the longest time, everyone's first instinct was fine-tuning. But let's be real, fine-tuning is brutally expensive and incredibly tedious. You're talking about tweaking billions of parameters. And think about a startup. Policies change all the time. You cannot afford to run a massive fine-tuning job every single time HR updates a leave policy. That's exactly where RAG comes in. It's cost-effective, you don't have to retrain a single parameter, and it effortlessly handles data that updates on a daily basis.
Which brings us to Section 2, the RAG solution. Retrieval-Augmented Generation is essentially the process of optimizing your LLM's output by forcing it to look at an authoritative external knowledge base right before it generates a response. Think of it like this. Instead of forcing the model to memorize every single fact through fine-tuning, RAG is basically giving your LLM an open book test. It takes the model's incredible natural language skills and applies them directly to your internal knowledge.
Moving right along to Section 3, the data ingestion pipeline. The big question here is, how do we actually get our messy private data into that external knowledge base?
This 4-step ingestion pipeline is the absolute foundation of your entire system. First, data parsing, reading your raw PDFs and HTML. Second, chunking, where we break that parsed data down. Third, embeddings, which is where we translate that text into mathematical vectors. And fourth, we store those vectors in a specialized vector database. Let's zoom in on that parsing step.
Before we even think about chunking, we have to parse our raw files into a document data structure. Now, this object has 2 parts, the page content, which is obviously the actual text, and the metadata. Do not sleep on metadata. This is all your contextual stuff, the file source, page numbers, author names. Tracking metadata is absolutely just as important as the text itself, because later on, it's what lets you run highly accurate filters, like telling the system to only search for answers in a policy document written by the HR director. And the good news is, you don't have to code these parsers from scratch. Frameworks like LangChain make this step almost trivially easy with their built-in document loaders. So whether you're staring down a folder full of messy PDFs, some random CSVs, or a SQL database, tools like the PyMu PDF loader will automatically grab the text, pull out the metadata, and wrap it all up perfectly into that document data structure for you. All right, Section 4, chunking and embeddings. This is where we break things down. So why do we even chunk? It all comes down to context windows. LLMs have strict, fixed memory limits. Let's go back to that HR policy manual we talked about. Say you've got a paragraph on leave, one on remote work, and one on expenses. You simply can't cram a 100-page PDF into a prompt. But here's the catch. If you use a basic, fixed-size chunking strategy and just blindly slice the text every 500 characters, it's going to fail hard in production. You might literally cut a crucial sentence about remote work right down the middle, completely destroying the semantic context. We need a way smarter approach. And for production, that smarter approach is usually a recursive character text splitter, like the one LangChain provides. It's the go-to default for general document Q&A. Instead of just a dumb character count, it recursively tries to split your text by paragraphs, then sentences, then words. You still set a chunk size, but you also set an overlap, say 200 characters. That overlap is your safety net. It guarantees that if you have a really strict policy statement on expense reimbursements, it doesn't get disconnected from its exception clause across 2 different chunks. Okay, once everything is chunked properly, we have to translate human language into machine language. We use open source sentence transformer models, like the super popular All-Many-LM 6v2, to convert your text chunks into mathematical vectors, which we call embeddings. This specific model generates a vector with exactly 384 dimensions for every single chunk. You are literally taking a paragraph's conceptual meaning and mapping it to an array of 384 numbers. It's honestly kind of mind-blowing. Next up, Section 5, Vector Databases Explained. We need a place to put all this math. Vector stores like ChromaDB or Fayus are purpose-built engines designed specifically for this. They hold these massive, high-dimensional embeddings right alongside your metadata. And the real magic is that they are highly optimized for similarity searches, using math like cosine similarity. This totally changes the game. When you search for a piece of text now, you aren't doing simple keyword matching anymore. You're mathematically finding the most conceptually similar information in your entire database. Finally, Section 6, the retrieval pipeline. This is where it all comes together. Let's walk through how this actually plays out in real time. Step 1. Your user asks a question about that company leave policy. We immediately run their text query through our embedding model to get a 384-dimension vector. Step 2. We take that vector and do a rapid similarity search in our vector database to pull the top 3 or 4 most relevant chunks. Step 3, we combine those retrieved chunks with the user's original query. And step 4, we feed that whole package to the LLM to generate a final, hyper-accurate answer. Now, how do we absolutely guarantee the model uses our data instead of hallucinating? We use prompt injection. We explicitly instruct the LLM, use the following context to answer the question concisely. We feed it our retrieved chunks and then the user's question. By firmly restricting the model to only use the exact, factual context we provided, we completely remove its need to guess. The hallucinations stop right here. And there you go. You now have the complete architectural blueprint to take messy, unstructured documents and turn them into a highly intelligent RAG system. If you're going to go build this today, here's my challenge to you. Try running your data through a standard recursive splitter and then try a more advanced semantic chunker. Compare the retrieval quality for yourself. It's a great learning exercise. So I'll leave you with this. Look around your org. Which of your company's messy data sets are you going to conquer and transform into a RAG pipeline first?